class for the master's portion. The reason we're doing like this is because your material is going to be slightly different from conventional ADSD, from conventional DSD because you are supposed to be taking the master's version of the course. So I'm going to be covering the last part So by agreement with Dr. Fauzi, the way your work is like this You still have your coursework and your extended assignment EA, the final exam equivalent. But for coursework, 30% of the grade will be from this assignment. 30% of your coursework So I think your coursework kalau tak silap should be 60% kan. So 30% or 60% is 18% So this assignment is worth 18% So what Dr. Palmizo agreed with me, and you let me know if it makes sense. Did he mention this to you or not There's going to be a final assignment for Budak DSD. They'll be focusing more on the tests and verification in this coming 3 weeks And you all are not going to be doing the test and verification because there is a full test and verification course under the MSc Dr. Palmizo yang ajar So that's how we make the split So instead, you're going to go a bit deeper into the design part, which is the FPGA Okay, so far so good.
Yeah, Doctor.
Okay, great. Right. So, Yihong, thanks for for highlighting this. I fixed this link already, so you can actually go through this textbook. You just click on it. It's there because they updated this So I'm showing you this because I just want to highlight to you this is a great book because it's got plenty of code. You pakai salin aja, so you will learn a lot. So if you actually go to part 1, it's actually very good already. Part 1, you can go to chapter 3. Chapter 3 is a general overview but I think it's more of the design examples I found is really great where they got this one basic design they show you how to write combinational logic, the different coding styles and then there's a decoder. This is using the module style, magnitude adder. So if you just go through the code here, the design examples, this is very instructive. You will learn how to write Verilog very quickly. So I would say normally for starting if your Verilog and circuit design is a bit weak, I'll ask you to focus on chapter 3, chapter 4, chapter 5, chapter 6. Okay, and it's not anything very new You should have covered this with Dr. Fangnizu already. It's just that this is just more examples of you look at it after a while, you more or less know the coding style It's more of getting you to learn this way of coding Verilog And today I'll cover a short. Today the lecture today will be primarily I want to go through SDRAM, synchronous dynamic RAM. We go through the details of the circuit and all that because your goal is you need to develop for your assignment an interface to control that and I want this tested on FPGA and I was thinking of getting this to merge with your lab 3 because your lab 3 you're using a RISC-V ALU and then you're writing to memory, right? ROM, RAM and all that, right? So now instead of just writing to plain old RAM, you'll be sending it to this SDRAM, which is a separate chip on the FPGA board. We'll talk a bit more about this tonight. But I'm just pointing this out because this is prerequisite. This you should have covered already in your first part of DSD. And this is the main requisite. You need to know this like the back of your hand if you want to get a job in IC design, whether in Intel or Micron or Opstar or Infinex or there are quite a few IC design companies around, or even FPGA company also. There's Phoenix and Penang and all that. So if you want to get a job there, then this one you really have to know. And I'll teach you to think about it tonight. I think we got a bit of time so to do that. But if you are not exactly sure, I would say you should focus on chapter 3, 4, 5, 6. These are the fundamentals. How to do finite state machine sequential circuits. And that should be it actually. That's the core. And then the rest are just to give you examples of IO core. They're full-fledged examples. For example, it tells you how to write a controller for SPI, for I2C, for PS2, PWM. So it's really very extensive this book. That's why I like it very much. very simple, straightforward to follow lah. So hope you get some time to scroll to that lah. But it's not a requirement lah. It's more of this is just learning material to help you lah. Today I want to focus more on this part here, and I'll put a copy of these notes on the site, the Ulan X. But basically where we're going is I've given you the FPGA assignment already, and I would really like you to be able to implement this on the Intel System Cloud for you lah. And I was thinking the easiest way to show you this, to give you the realism is from your lat 3, you have a Verilog for RAM, register file, ROM, right? Is it the Verilog to implement RAM or the Verilog to write to RAM? What are you doing for lat 3? Can you tell me?
I think it's about how we build the RAM itself.
How you build the RAM itself. So it's a RAM emulation lah. But how are you writing to RAM?
We just input some random values inside the test bench, and then we
Okay, I see.
we observe in the waveform.
So you're just doing ALU. You're not doing the full RISC-V lah anyway, are you?
Not yet, I think.
For lat 4 for RISC-V.
The assembly part we'll be doing it in lat 4.
Okay, so RISC-V is that. Oh, you have to write assembly code and then you compile you synthesize the RISC-V in at processor, is it?
For lat 4, basically just combine the ALU, ROM, RAM, and register file, and then we combine it together and make it as a mock RISC system.
A mock RISC, I see. Okay. So I think where I'm asking you to interface this the best would be you just take ALU and you write your ALU actually has a fetch and write, right? The ALU. Are you doing fetch and write? Do you have a fetch to register and then write to memory? Do you have those commands in your ALU?
No, I just assign random values and then just do the arithmetic operation, the shift right, shift left, yeah.
Oh, so I see it's logical and adding lah, but you haven't you didn't do any kind of writing to memory and all that lah. Do you all, but so you all don't do the instruction decode and fetch, you all don't implement that lah?
No, haven't, but I think lat 4 we will need to implement that part.
Okay, lat 4 is when?
This Friday. Actually, we are doing this Friday. Is another session, if I'm not mistaken.
This Friday lah. Okay. You can keep in touch with me lah, because I said this is the first time I'm giving this assignment. I don't know how difficult or how easy you will find it lah. I want to just try to make it the easiest possible, but my baseline is I need you to design a circuit to interface to the SDRAM chip lah on the FPGA. Now, whether you are doing it from just, you're just doing the controller, you're not interfacing to any processor or ALU, or whether you're using ALU from lab 4 or whichever lab, you let me know which is easier or more straightforward for all of you. But I hope you all can actually develop the logic in order to interface with the SDRAM lah, and that's the goal lah. So submission actually requesting from you a Verilog RTL file. So a test bench and simulation result. So you can do this on EDA Playground, or basically here what I've done is there is this software part here, and I've given you this Docker image, and this Docker image inside already pre-installed Icarus Verilog, Yossi's Qflow all lah, but you can actually just run the Icarus Verilog simulator. You just run this lah, but you have to learn how to use Docker lah, which is a good thing to learn anyway nowadays lah. So this is an alternative. If you want to do the simulation on your machine, you need to install Docker. You pull out this, and then when you run this command, it's like you're going inside a Linux terminal, and that already has the tool Icarus Verilog all installed on it. So either you do it on EDA Playground or that. But what I'm looking for, as I mentioned to you, the Verilog RTL file, the test pen and simulation, and I want a demonstration on the system cloud for you system lah. So whatever you have on your test bench, you implement in the system cloud for you on the real FPGA. If it works, great. And the idea for this is basically, this is one of the more challenging tasks around, but it will definitely give you something great to talk about for your interview lah, your job interview, if you can even talk about interfacing to SDRAM, because now this is no longer SDRAM, they talk about DDR-RAM. But let me know how you all are doing with it. Don't wait too long, like by the end of this week or early next week, let me know how you're coping with this. We can still adjust it a little bit lah. And I think yeah, I think that's what I'm just worried about lah. And you know, just you have to really like learn your Verilog really well lah, your Verilog circuit design lah. So there are a lot of resources here, but my worry now is just basically time lah. I think the worst case, I set the deadline to be 30th July. I think your extended assignment is 2nd of August, is it? So is it 2nd of August?
Yeah, our final exam is on 2nd of August.
2nd of August.
At
Okay.
the morning session.
Okay, so I don't really need you to do this on your own. Would you prefer to work in a group of 2 people, or would all 4 of you prefer to work in a single group?
I think all of us need to speak. I cannot just speak on
For me, I would prefer for all of us work with in a group. So.
Yeah,
Okay.
for me also.
Because of the complexity of this, actually, this if you've got more time, you can actually work in group of pair or single person. But because of the complexity, and I don't know, you still have work, I'll let you work all 4 of you to do one group, one submission. But I need you to say who did what part, and I cannot have you all be riders lah. Cannot lah. For the
so-
simple reason, yes. Yeah.
Sorry for interrupting. But so basically for this assignment, we need to design the SDRAM which contain the ROM, RAM, and register file.
No. The SDRAM chip is already on board. You need to design a circuit to read and write from the SDRAM chip. Okay. So what you have in Lab 3 is a very simplified version of a RAM. It's usually what they call, at least is static RAM lah usually. But now we're talking about dynamic RAM. Actually, we're talking about synchronous dynamic RAM. We're going to go through the details today of what makes it challenging and why it has to be designed that way. The main reason is because of speed. The kind of RAM that Dr. Fantizu covered in Lab 3, nobody uses that anymore lah, to be quite frank lah. Why? Because it's too slow. Right? If you're just relying on the address and then you want to read out from that, it's very slow. You can't read many words fast. So nowadays, modern RAM chips, they don't just have the RAM array inside. They also have a controller, and usually it's a state machine actually. So there's like a full, you can think about it's not quite a processor, but it's a full state machine inside there that is controlling the access today. And we'll go through the architecture today. That's what I intend to cover today, to give you this understanding. It's a crash course, but there's no way about it lah. Okay, so what you're covering in Lab 3 is, I would say, this is not how we do RAM and ROM. It's probably not how we do register file as well.
Okay.
But it is a way to simulate RAM, ROM, and register file. But this is not how anybody in industry, in the chip industry, and nobody does it this way. Okay, that you have in Lab 3, nobody does it this way. It's just a teaching tool to help you to understand that you need an address, data, all this kind of, but nobody does it this way. And this is not how you implement RAM and ROM, because RAM and ROM are special purpose designs. There's a separate design for that. What you take care of is the interface, right? And we are talking about one very common industry standard interface, which is quite old already. It's not used anymore actually, SDRAM, but it's the precursor to what they call DDR-RAM. And I'll explain a bit how is it similar and how DDR-RAM is a little bit more complicated than SDRAM. But if you can understand SDRAM, you have an entry point already into the industry to be able to design like memory interface circuits and all these things, the digital circuit. So you have to understand that your lab 3 is a simulation, it's not realistic, it's not real. Register file, I'm not sure if people do this anymore. In the old days, maybe if you talk about 20 years ago, maybe they still do it because you synthesize flip-flops. But in today's day and age, I actually believe they just built static RAM. I will cover what static RAM is. I'll let you know what it is. It's just that the difference is in the cell. What is a unit of, how is a single bit stored? So in this Verilog RAM and ROM, the single bit, actually you're not even taught how it's stored. They just write a code that simulates it. But if you synthesize it, it will synthesize into flip-flops, okay? Because of the always block. But in real life, you don't use flip-flops. You actually use a cross-coupled inverter as the base of your 60 cell, and you use a capacitor as the base of your DRAM, dynamic RAM. So that's the difference. But yes, what I would like you to do is I would like you to design and test out and show a working circuit that can read from SDRAM. And this is an SDRAM chip. It's not a play simulation. It's a real chip with timing and all these kind of things. And write to SDRAM. And if you can manage it, I put the third thing is actually you have to also do the prefetch that you read, write, and refresh. But if you cannot manage read and write, is also enough already. I just need you, and you don't have to do all cases of read and write. Just one case is enough. Okay. But you can have to try with different values. It's just to get you into this, really had the hands-on to be able to handle timing and all that. Okay. So that's the key. Okay, and you can interrupt me if you're not very clear. But basically, you would first need to reference section 3.6.10, this FPGA board documentation, this PDF. It just shows you the pinout of the SDRAM. Then there's the textbook called Jacobs, which is this one. This whole textbook is all about memory systems design. I'm asking you to read section 7.2, 7.3, 8.1 to 8.8. This second part here, this is just background understanding. The key part to understand how to interface the timing is in chapter 11. So you read 7.2, 7.3, 8.1 to 8.8, and all of chapter 11 from this textbook. Then you get the data sheet from the system cloud for you, and then you start your design. That is the process. Okay. I am not able to extract the data sheet because I made a stupid mistake last Friday. I was trying to link up to System Cloud and then I deleted my Pulse Secure and I can't log into the thing anymore. So I ask your help if any of you are able to log in. If you can go to there's a directory there and that you can find the data sheet. You can pull out the SDRAM data sheet, you send that to me so I can reconfirm. I can put it here and then we are on the same page because otherwise I'm going a bit blind. I have to use a different data sheet actually. And it's not great, but it's okay. It's not great, but it's okay. Okay, let me check Micron SDRAM. Is the assignment clear?
Maybe I need to go through it first before I know what I'm not clear or clear with.
Okay, that's fine. That's fine. That's fine. Please do that. Give me feedback. Okay. So if everything is okay so far, I'm going to start my lesson already to talk to you about SDRAM. Okay. Okay. Before that, I think I'm missing one introductory section, which is basically this idea of memory. When you talk about memory, you always say RAM, right? And I think all of you are probably familiar now, based on what Dr. Faumizo has given you. RAM, you have address, right? You have address bus, correct? I have address. And I'm just going to make this a very thick line to indicate it's a bus. That means it's not a single bit. It is like 16-bit, 32-bit, 8-bit. That's okay, right? You can follow that, right? Big one here. And feel free to stop me anytime if you don't understand anything. Okay, so we have address bus here. And we also happen to have another bidirectional bus. Okay, this one has two direction. Why? Because you need a start arrow here, because this is my data bus. Then you have a third one, which is the read and write enable. And then sometimes you have chip select lah. But chip select is less important because it becomes important when you're actually combining this to make a bigger word, right? But I would just say maybe it's like read, right? It depends on the logic lah. If you said read bar write, means if it's logic 0, whatever address is being read from. If it's logic 1, right, whatever address you're writing to the address, right? That part is clear, right? So far is so good, right? So you just put address, and depending on whether you are saying read or write, you're either putting a data in or you're reading a data out. Okay, and that data could be 8-bit, 16-bit, and all that lah. And I like to always encourage people to think about this RAM as, okay, let me look for. I'd like you to think about it as a bunch of boxes lah. Instead of this black box, it's basically really a bunch of boxes. Okay, you can think about it as just a bunch of boxes. How many boxes? Well, the number of boxes dependent on the number of address bits lah. If I have 4 address bits, okay, 3 to 0, I have 4 address bits, means I have 2 to the power of 4 or 16 boxes lah. Okay. Because 4 address bits, I can have 16 combinations. You follow me? 0000, 0001, 0010, 0011, and all that lah. So each combination refers to one box. Can 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. So this has 32. So this actually has 5 bits of address, right? Because there are 32 boxes. Now, depending on the content of each box, let's say the content of each box is 2 bits. Okay. Then your data line is actually a 2-bit data line. Okay. If the content of each box is 4 bits, then it's a 4-bit data line. You follow me?
Yeah.
This part is not new, right?
Yeah.
Is it okay?
Yeah, understand.
Yes.
It's not okay, you can ask me to repeat. I can repeat it or try to explain a different way.
Yeah. For me, okay, Doctor.
A bit of feedback, or you guys are busy? If you just want me to talk, I'll just talk lah. It's okay lah. I won't ask questions.
Understand. Yeah, we understand what you.
Sorry, can't hear anyone.
Hello, Doctor.
Hello.
Iman, I think you're trying to say something, but I don't hear anything.
Oh. Hello. Can you?
Sorry. I'm muted. Can you try again?
Yeah.
Hello, sir.
I understand.
Okay, sorry.
Yeah.
I don't know how I ended up muting my speaker. Sorry, must be late now. You understand, right? Okay, so great. We have the basics of memory here, and usually when you come across this memory, most people will talk about the 60 SRAM lah. And SRAM actually stands for static random access memory. Okay, RAM stands for random access memory. Why? Because the fact that you're using addresses, you can access any box randomly. Right, you don't have to access in sequence. There's some types of storage that you need to access in sequence, like hard disk, not SSD lah. SSD is probably random access already lah, right? Because it's semiconductor. Like the hard disk, the disk platter, that's actually sequential access. Magnetic tapes, nobody use tapes anymore. CD is actually sequential access, right? But this is random access. That's why you have an address, because the address lets you go jump directly. Okay, this is a picture of what we call the 60 static RAM cell. Why is it called static RAM? Is because this cell stores 1 bit. You will take 6 transistors to store 1 bit. Literally, if you have to start to learn to recognize, this is an inverter, this is an inverter. So it's actually a cross-coupled inverter. Yes, this is what it looks like actually, right? And there's 2 lines. They're called the bit line and the bit line bar. Okay, so the word line, later we'll talk about it. What happens is this is the true value of the bit that is being stored by this circuit, and this is the complement of the bit being stored by the circuit. And you can, if you read it out, this goes onto the data line. And if you're writing something in, you got to turn on this transistor, and then the data will actually go in and change this. But your storage element for static RAM is actually two inverters in this fashion. It's called cross-coupled inverter. And the transistor form of this is actually this one. Is actually this one. Okay, right. It's called 60 because in order to, and it's called static is because in order to save this bit, you're actually actively consuming power. This one actually actively consuming power. So if the bit starts to leak, there's going to be power because these inverters here got power, right? There's a VDD and a ground, or VCC and a ground powering them. Okay, so one bit is 6 transistors. So you can imagine if you've got 8 bits, is 8 times 6 transistors. So it's 6 transistors lah. So for this, and normally static RAM is used for only the memory that is fastest or closest to the chip lah, to the processor. Normally you use static RAM for registers, or you use static RAM for L1 cache, level 1 cache, CACHE lah. Level 2 cache onwards, most likely you'll be using what we call dynamic RAM. Okay, what is dynamic RAM? Dynamic RAM is a different form of RAM, okay, where instead of 6 transistors like this, we are using only 1 capacitor and 1 transistor to represent 1 bit. Okay, so you have a 6 times saving lah. I think not quite 6 lah, maybe 5.5 lah, or 5 lah. Why? Because most likely this capacitor, it can actually be just made from a transistor lah, right? Because this is actually just literally a capacitor lah. This is actually a capacitor. The gate and the substrate here, if you tie the drain and the source together, then this becomes a capacitor. So sometimes this is just a MOS transistor. Okay, so instead of 6 transistor, I can represent 1 bit with 1 capacitor and 1 transistor lah. This is called a pass gate, right? Because if I want to read, I have to turn this on this gate, then the charge will flow out. If I want to set this, I turn on this gate, the charge will flow in. If I turn off this gate, not conducting, this capacitor is going to hold charge. Okay, so this part also, so far so good, right?
Yes, sir.
Okay, now you start to see a problem. You're putting a small charge on the capacitor. It's not even 1.8 volts here. This is several tens of millivolts to hundreds of millivolts here. That's the amount of charge across here. What happens if you leave this capacitor for a long time? What do you think happens? Will it retain its voltage?
Minimum voltage.
I'm sorry, can you repeat that?
Retain minimum voltage.
What did you mean by minimum voltage?
Voltage.
Okay,
Yes.
so it will retain. How long will it retain the voltage?
Not long.
Ah, very good. Good. Follow your intuition because you are already 40 already. You're right. It doesn't retain voltage for long. It leaks, right? You know this from all capacitor. They leak. If you leave this for a while, after a while, you'll go to 0 volts, right? And that's the problem with dynamic RAM, because once you charge it, dynamic RAM is leaky. You can't leave it for long. You have to constantly refresh, which means you check what is the voltage here and then you top up, you top up, you top up. Whereas static RAM, because you see the inverter is always connected to VCC, is always holding the value steady. So the 6 transistor is expensive because it's got 6 transistors rather than 1, but the value is very stable and all that, and it's fast because it sucks power like anything. Whereas the 1 transistor DRAM is very cheap because it's like 1 transistor and 1 capacitor is like very small, but you have a problem that it leaks. Okay, so when we talk about DRAM array, it's just an array of bits, right? So each of these boxes, you can think about it as 1 bit. Okay, so if it's a static RAM, each of these box is this 6 transistor. If it's a dynamic RAM, each of these boxes is a single capacitor here with a transistor. Okay, and the way RAM is organized is actually in a grid fashion like this, right? So you see this is 1 bit, this is 1 bit, this is 1 bit, this is 1 bit. Okay, and then you see the bit, this is called the bit line because this is the bit is going to be read out here. Okay, the bit's going to be read out here, the bit's going to read out here. So depending on which bit you select, okay, it will be read out here. And how do you select which bit? you turn on this line, or you turn on this line, or you turn on this line, or you turn on this line. You got it? So this one output here, okay, can choose between this bit. You got that? And the way I choose which of these 4 bits is I select which of these lines to turn on lah. Logic 1, right? Because logic 1 will pass this. Logic 0, it won't pass lah. It's like a off switch. You got that?
Yes.
So what actually happens is I got a bunch of these outputs here, okay? And all of these bunch lists 1, 2, 3, 4, 5, 6, 7, 8, it will go into another level of multiplexer here, and then you will choose which of these, okay? So your DRAM is accessed by having a row select, which is the word line. I'm choosing which row. And you have another column select, which is choosing which of these outputs I'm going to ultimately send out to my 1-bit output. You got that? So what I'm actually now showing you is a dynamic RAM array can only send 1 bit because yeah, it's storing 1 bit. Even the static RAM also is storing only 1 bit. It's just got true and the complement of it. Okay. And the way you choose which bit you are addressing is you select a row, which is enabling this, and you select a column, which is choosing between either one of these, which means therefore that your address, you are using your address to select the row and the column. Now you understand why I'm drawing it this way, because I want to differentiate to you that in DRAM and also in the static RAM, it's the same also in static RAM, but we're talking about DRAM specifically now. In DRAM, you have to choose the row and the column. So this one row, or this, let's say I go back and I don't put 4 bits here. I just say it's 1 bit. Okay. Okay. Now you can see that this whole row, 1, 2, 3, 4, 5, 6, 7, 8, this whole row is equivalent to 1, 2, 3, 4, then 5, 6, 7, 8 lah. Okay. So that whole, sorry, just got confused a little bit. This whole row, okay, this is between, sorry, mistake. That whole row is this one, 1, 2, 3, 4, because I will need to choose the row itself will select all of them, then I will need to choose which bit is coming out. Okay, so this whole row, this transistor, this capacitor and transistor, this capacitor and transistor, this capacitor and transistor, this capacitor and transistor will represent this. So it's up to me as the DRAM designer. So you're not designing DRAM. This is what the DRAM chip manufacturer they design. They will split your address bus into 2 parts. One part of your address will be used to address which row, whether it's the first row, the second row, the third row, the fourth row. And another part will be used to address which column, 1, 2, 3, 4, 5, 6, 7, 8. So here you see I've got 4 rows. That means I only need 2 bits to address all 4 rows. And I've got 8 columns. It means I need 3 bits to address each column. So 2 bits plus 3 bits, 5 bits, right? So my address has 5 bits. Okay. So it's up to the DRAM designer, up to me as a DRAM designer, not you. You are not going to design this for FPGA, but I'm just telling you how it works. You can choose the 2 LSB to index these 2, and then the MSB here. You can choose the 2 MSB to index these 2, the LSB here, or you can choose some bit in between to index these and these. It's up to you. It's equivalent one. But what I'm just trying to say is the address bits are normally partitioned out to be split out. Some of the address bits will be addressing the row select, and some of them will address the column select. Do you get me?
Yes, sir.
Yes.
Okay, great job. So that's why you need a word line and you need a bit line, because the bit line is everything in the column. The word line is everything in the row. So the way you access this is you turn on everything in the row, okay, the word line. So all the bits in the row are going to go to all this amplifier. Okay, so the whole row, all the bits are being read out to the amplifiers. And then the column itself, the column choice, the address of the column will choose a multiplexer. One of these bits only will go out. Okay. Now, we're only talking about 1 bit because we've mentioned here the DRAM is only 1 bit, right? It stores 1 bit, is a 1 bit box, okay? How do I get 8 bits, right? Because your DRAM is like 1 byte, 2 byte, 3 byte, 16 bits is 2 bytes lah, 32 bits is 4 byte, 16 bits is 16 bits is 2 bytes, 32 bits is 4 bytes, 64 bits is 8 bytes. How do you do that? You have 8 of these arrays in parallel. They share the same row select, they share the same column select, but they're selecting 1 bit from each array. So if I want to read a data word, I have 8 boxes like this, but I use the same address lines, that means the same row and the same column select to choose the data word. So you understand that?
Yes, Doctor.
Can, okay. Okay, sorry, I just need to keep checking with you because we're moving very fast. So if you don't understand, you have to check. You have to check with me. Okay, so this is how DRAM works. Okay, I will come back to this. Okay, this is how the basic principle how DRAM works. This is how it is accessed. This is how it's organized. Now I'm going to tell you something interesting. Just now we told you that this capacitor is not held at 1.8 volts or 1.1 volts, or yeah, definitely it's not at 3.3 volts or 2.5 volts or any of those CMOS volts. It's actually a few tens to few hundred up to 100 millivolts only. So you're going to be asking me, okay, Dr. Ho, if it's only 100 millivolts and then it reads out here, what do I actually read out here? It's like 100 millivolts. That's like logic 0. So logic 1 is logic 0, logic 0 is logic 0. I don't get it, right? And you'd be right. And this is how it's actually done. The charge that is stored in each capacitor is actually really small, and there's a reason why we store a small amount of charge. Small amount of charge is easy to move, so your DRAM can respond very fast. If your DRAM is very large amount of charge, either the capacitance is very big or the voltage is very high, it takes longer to read it out because you have to transfer more charge, source more current, takes more energy. Okay, so it's a speed and energy argument. We like to keep the amount of charge and the voltage stored by the charge small. So what happens is this small amount of charge is going to change the bit line a little bit higher, and this sense amplifier is doing a very interesting job. Number one, what it's going to do is this sense amplifier is actually drawing power from VCC and ground or VDD and ground. So when it sees that it's slightly higher, it's going to actually amplify it until it becomes a full logic 1, which is 1.1, 1.8 volts or 1.1 volts or 2.5 volts. Okay, so you understand why I'm saying 1.1, 1.8, 2.5, 3.3. You understand, right? It's because digital logic nowadays, you have different logic families. It's like super old from the 80s. If you talk about TTL 5 volts, that's from the 80s. Bipolar transistors. CMOS, you talk 3.3 volts. This one discrete circuits. Almost no circuit that is expensive and high performance is at 3.3 volts anymore except if they're very cheap. Most likely you have a 2.5 volt CMOS, you have a 1.8 CMOS, and you have a 1.1 volt CMOS. The VDD is 1.1 volt, is 1.8 volt, is 2.5 volt. So naturally, depending on what the VDD is, that's logic 1. So what this sense amplifier does is it detects the slight increase in voltage here by few tens of millivolts to 100 millivolt, and it will output here logic 1 at whatever that CMOS volt is. So the sense amplifier actually plays two roles. One, it actually really amplifies it to a full digital logic. Number two, this sense amplifier acts like a buffer, like a flip-flop. It's actually storing the value of whatever is read out until the next time you update it. You got it? This is the role of the sense amplifier. Okay?
Okay.
Okay, great. Now it's going to get very complicated very quickly. So given that I told you that the way we access this is basically we have to turn on the word line and we have to turn on the correct bit line we have to choose. And then there's this sense amplifier magic that's actually reading a small value of charge. And then you'll be like, if you're a little bit sharp, you'll be like, okay, you know, you're reading this out. So you're saying the charge is going to discharge out and then it's going to raise this bit line. But once the charge come out here, this bit line goes up. Didn't I just use up the charge in the bit? But I'm supposed to store the value in the bit, and you'd be right. Reading out from a DRAM is actually a destructive process. you remove the charge from the capacitor, and then the data is gone. So after you read it out, there needs to be some kind of clever mechanism to restore the data back in. So you can see you're paying all this kind of funny trouble just because you're moving from 6 transistors to 1 transistor. You don't have all these funny transistor problems with the 60, right? When you read out from a 60, it's like digital logic. You just read it. The bit is always going to be set there unless you change it. But from a DRAM device, because it's a single capacitor, when you read it out, you destroy the bit. So you have to update it. So you have 2 funny issues here. 3 funny issues here. Number 1, your bits are not actually at the full logic 1, logic 0, unlike the 60 transistors, which they are. Number 2, when you read the bit, you destroy it. So you have to find some way to restore it. Oh, bummer. So it's another crappy thing. And number 3, even if you don't read the bit's going to disappear after a while. And specifically, it disappears in every millisecond. You have to refresh this every a couple of milliseconds. Okay, so you have 3 things that you have to take care of just because you're going to a single capacitor rather and 1 transistor rather than 6 transistor. Is it worth it? I would argue, yeah lah, the industry found it worth it. Why? Because you can compare the difference lah. If you're only going to be using a 60 transistor, you can get maybe a 1 megabyte cache. But if you use a 1T transistor, you may actually end up getting a 6 megabyte cache. So you've got like between 5 to 6 times the capacity if you go for 60 lah, which is a lot lah. It's not a small amount lah. So that's why people are willing to go through all this trouble. So now we'll go through the gory details of how do you actually read and write into a DRAM bit. Okay, you're not going to be doing this in Verilog, but I need you to understand this because where we're going at the end of the day is I'm going to tell you that this is your DRAM array, and that's what we've been describing, but you have all this additional digital logic, which is the controller that is sitting on the chip, on a DRAM chip and SDRAM chip. Okay, and what you're doing is you're going to be writing some extra logic here to send all these digital inputs here in order to control, read and write from this DRAM. Okay, and it's a bit complex, and it's actually going to be starting to sequence a bunch of commands. It's not just you put the address you get. When you interact with, when you interface with modern SDRAM, you are actually sending it a bunch of commands. So it's quite similar to what you would do on a bus with a processor, on a bus with like a sensor. Let's say you've done I2C or SPI programming. It's like you're sending command and then you're getting response, command and response. So you're going to be doing that with the SDRAM. You have to design that circuit. So I have to go through all these things so you understand. Okay, so this is how DRAM is read. Okay, so now what I'm showing you is I'm actually just showing you 4 bits of the DRAM. Okay, 4 bits. Let's say 1, 2, 3, 4, and they're going into a sense amplifier. Except that now the sense amplifier, now they're showing you this is the circuit. And then there's another circuit called a voltage equalizer circuit that's going to equalize 2 bit lines. Okay, and the key point here you have to note is 1 bit. Okay, 1 bit, actually there are 2 bit lines, a bit line and a bit line bar. Okay, they're always pairs of bit lines. They are taken together. So again, this bit line is paired with this bit line. So one of these will be positive logic, one of these will be complementary. That means here logic 1 is logic 1. Here logic 1 is actually logic 0. Okay, and that's what's represented here. There's a bit line pair, and it's going inside the sensing circuit, right? Because this is the sensing circuit. It's called the sense amplifier. And you remember that the sense amplifier has 2 roles. One is to bring the small change in voltage here to the full logic, and number 2 is to buffer, to actually hold and remember this value. Okay, so I want to actually get your attention that this bit line is actually your data. Okay, so you are sending it out to the output. So here you see this is the bidirectional driver, right? You're either sending it out or you're receiving data in here. So if you turn on this transistor, there's a logic 1 on this line, the data will be read here. That means you have to make sure that the output, there's nothing here. The data will be read here. If you turn this off, the data can be sent out. And then that's why this is called write enable, you see. So if the write enable pin is turned on, you are letting the input line, the data input, to actually drive this bit line. Okay, if write enable is 0, you are just reading from whatever value of the bit, you're sending it to the output line. And this is actually the chip select. So you can see the chip select is just basically you're connecting or disconnecting the DRAM to the output line. That's all. Okay, this is a chip select. All right. So the first step before you do anything, you had to do a pre-charge step. Why a pre-charge step? You become evident as we talk about how the read process is, but basically it's got something to do with the fact that the voltage that you are storing in each DRAM is actually a very small amount, like 100 millivolts around that. Okay, so what you actually do is when you do the pre-charge step is you make this bit line and this bit line bar, you make it the same voltage. It's called the voltage equalization. And what is that voltage? Normally, conventionally, this bit line is going to be VDD divided by 2. Okay, so if you're at a 1.8 volt process, this is going to be held at 0.9 volt and 0.9 volt. Both will be held at 0.9 volt. So how is it done usually? Well, it's going to have this equalized symbol here, and there's going to be VDD over 2 here, driving over 2 here. Then you just turn on this transistor, and this transistor is going to force both lines to be same, VDD. Okay, and you're also going to have this transistor here. You're going to also force them to be at the same voltage. But the key point you have to remember is the pre-charge step. What you are making this bit line, this wire here called the bit line, which is connected to the output and can also receive input. But because we are reading, is connected to the output. Don't worry about the input yet. We'll talk about that later. And so at pre-charge stage, which is stage 0, is held at VCC over 2. Okay, here. Is called pre-charge. Okay. Now, after your pre-charge, you're going to be starting the read process. The read process is actually broken down into 3 steps. It's called access, sense, and restore. Okay, access just means I am now going to choose the word line and have it to update my bit line. Okay, so again, this is only 1 bit. Okay, this is only 1 bit. Okay, 1 bit line here. Okay, so if I choose the word line, that bit will update lah. But again, when I choose the word line, I'm actually doing this same process for all the bits on the word line. It's all the bits on the row. It's happening at the same time. Okay, but I'm just showing you here the circuit is only for 1 bit here. Okay, so this bit line, what happens? It's the word line is selected this particular transistor, this particular bit. This one is not selected, this one is not selected, this one is not selected. So it's going to read out this cell. So there are 4 cells here. I'm only going to read out this cell. Okay, and this cell is held at logic 1. So what's going to happen is this charge here is going to discharge, is going to equalize, right? Because this voltage is going to be slightly higher than VREF. Okay, it's going to be, it's going to be slightly higher than VREF, and it's going to discharge onto this line. Okay, it's going to discharge onto the VREF line. It's going to raise VREF slightly. Okay, so when it raises VREF slightly, what happens is very interesting. When you raise VREF slightly, okay, you see all of a sudden, you raise VREF slightly, okay. VREF goes up a little bit, and this one goes up a little bit. So, sorry, it's a bit late. Okay, yes, that's right. Okay, here. Okay, this one is going up a little bit. So this initially this line and this line were the same voltage. So this transistor is turned off. But when this VREF gets turned on ever so slightly, and it's actually going to be V threshold higher, this voltage here is going to have to be greater than V threshold of this one. This transistor is going to turn on. And then when this transistor turns on, what happens is this bit line is rapidly going to discharge to logic 0. That's why the SAN line will discharge to logic 0, because there is a line that is connected to here. Is going to rapidly discharge the bit line. This is going to be logic 0. It's going to discharge this bit line to logic 0. And when this bit line is discharged to logic 0, this PMOS will turn on. And this SAP is actually logic 1, the 1.8 or the VCC is going to charge up this bit line to logic 1. So what's going to happen is now I'm explaining to you, because there's a small change in charge here, that small change is enough to turn on this sense amplifier circuit, basically this one and this transistor. And what happens is it will rapidly discharge this bit line and charge this bit line to logic 0, logic 1. So you go up here like that, go down here like that. Okay, this is the job of the sense amplifier. You're seeing is now amplifying the signal to logic 1, logic 0. And the opposite will happen. If this is a logic 0, if this is logic 0 here, okay, if this happens to be logic 0, this is logic 1. So if this is logic 1, this transistor will turn on and will rapidly discharge this line to logic 1. Okay, then this line is logic 1 now. This line is logic 1 now. It will rapidly turn on this one. Okay, this, and then it will discharge this to logic 0 lah. Okay, the inverse will happen. Okay, so what I'm trying to explain is there is like a positive feedback lah, like just a small change in the small difference in the bit line voltage is enough to rapidly tip the voltage here to logic 1, logic 0 lah. Okay, so once in logic 1, logic 0, you have the value at your output already. So this is how the read is done. Okay, but when the value as the output is there, remember this bit is, this word line is still turned on. That means this logic 1 line has now gone, just now it discharged a little bit, raised the charge here slightly higher. Then when you are turning on this line suddenly charges all the way to logic 1. When this is like logic 1, is going to charge back the capacitor here, the restoration happens here. Okay, and the converse is true. If this happens to be logic 0, it's going to discharge this transistor, this capacitor all the way to logic 0. So this is how I'm explaining. This is the process of one DRAM read bit. You need to pre-charge, which is basically equalizing the voltage of the bit line. You set that as not logic 1, logic 0, but somewhere in between. Then you turn on the bit that you want to read by selecting the word line, the row access. That gives a small change on the bit line. The sense amplifier circuit rapidly drives the bit line to logic 1, logic 0, and then it's ready to be read out, and it also restores the bit value onto the capacitor here. Okay, that's the restoring part. So this is a DRAM read process. We're going to go ahead and talk about DRAM write. DRAM write, the opposite is happening. What happens is now you have to turn on this write enable. You put in a value here, logic 1 or logic 0. I mean, this is the complement. So you put in the logic 1 here. Straight away, the logic 1 will charge the capacitor here of whatever bit you select here. So DRAM read, you need the pre-charge to actually equalize the bit line so that you can use the capacitor to tip one or the other. Then you do the access, the sense, and the restore. DRAM write, you don't need to pre-charge because the line will actually be set to logic 1, logic 0 by your input. Okay, you directly will just charge the transistor to whatever it is. All right. So at this point, do you have any questions on the DRAM read or write process?
For me, I'm okay.
You're okay, huh? No, sir. Okay, so anyway, this is recorded. I'll share this. So as you can see, it's a digital circuit, but there are a lot of analog components in it. And the whole point is because they want to save power and they want to speed this up, right? And they also can save on size because if the capacitance is small, each bit can be held very small, right? If I make this capacitance small, one bit is going to be really, really small. Then I can charge it faster, use less power and all that. Okay, right. So as you can see, the important step is besides this, the reason I'm showing you this is because now you will later understand that I cannot just put the address on. I actually have to pre-charge first. Okay, I put the address, I have to give it some time to pre-charge, then I have to give it some time to access, to sense, to restore, and then I have to restore the value again, and then I'm pre-charged, right? So a write is not just, I have to give it some time to do all these things. I cannot just expect the value when I'm reading to be instantaneous back to me. And same with the write process, I cannot also just put this on and expect it to be instantaneous because when I put give it time to actually charge the bit line, right? So it will go through the access, the sense, and the restore phase, and then you do the pre-charge in readiness of reading. Okay, so you need to pre-charge before you read. For writing, it's not necessary to pre-charge, but usually what happens is they always pre-charge after that. They don't pre-charge before they read. They pre-charge after every operation. So after a read operation, you pre-charge. After a write operation, you pre-charge, right? So because you get ready that the next operation, if it's read, you can start the read, the access, sends, and restore. So this starts to hint to you already that there is a sequence of timing that you have to respect when you read or write DRAM because of the nature of this circuit. Now, I'm just going to briefly go to talk about address decoding, because as I mentioned to you, again, we are saying that if we have 4 rows and 8 columns, I must have some kind of circuit that will convert the address into whether choosing row 1, row 2, row 3, row 4, column 1, column 2, column 3, column 4, 5, 6, 7, 8. I must choose between those two. And that circuit is called a circuit, okay? And usually you can use a NOR gate or a NAND gate. A NOR gate, if it's all zeros, then it is logic 1, and then other than that, it is logic 0. A NAND gate, if it is all, a NAND gate, not AND, if it's 0, 0, 0, 1, 1, 0, it's logic 1, otherwise it's a logic 0. So most likely the decoder usually is made out of NOR gates, because NOR gate will only be 1 if everything is 0, right? So they will choose address or the complement of the address line. So you will have one of these NOR gate for every row. Every row you will have one of these NOR gate. Why? Because the first row is selected by 0, 0, 0, 0. So for the NOR gate, you need to put not all 0, 0, 0, 0, okay? Then you will have logic 1. The second row, if it's selected by 0, 0, 0, 1, you will put 0, 0, address 0 is 0, address 1 is 0, address 2 is 0, then not address 3. That's the 1, okay, if you want to select the row 2 and row 3 and all that. So you have this huge decoder circuit, 1 for each row. And later on, you also have a similar circuit for the column select. The column select is basically you're choosing which of these sense amplifier output you're going to sending up to the bit. Okay, so there are the two parts to it. And this is just actually showing you that because of the reliability issue, normally in circuits, they will actually have a spare few extra decoders which you can turn on, turn off by laser fusing. But I won't talk about this. It's not absolutely key. If you're interested, you can read the Jacob's book. So just to share with you, this is how address decoding is done. There's all these circuits that will decode the address. So if you have n bits address, you'll have 2 to the power of n bits, 2 to the power of n decoders. So if I have a 4-bit row address, all right, then I'll have 2 to the power of 4, I have 16 NOR gates. Okay, and again, this NOR gate is a 4-bit row address. This NOR gate will have to take in 4 bits. Okay, if it's an 8-bit row address, I have 2 to the power of 8, 256 NOR gates. Each NOR gate has to be 258-bit input. Okay, but of course, I won't have an 8-bit input NOR, so I will start to break up the 8-bit input NOR into a cascade of 2-layer, 3-layer, 4-layer NOR gates. So you can see that the circuit can become quite big to design. Okay, so how is DRAM access? Okay, so now that you understand that I have to select a column, okay, first I have to select a row. The word line is a row. I select here. Then I have to choose which column, which bit to select. So there's a row select and a column select at the multiplexer. Okay, so in order to access the DRAM, I would need a signal that selects the row, a signal to select the column, and the write enable. And this is the standard, what they call the asynchronous DRAM. And this is what you typically will do one step after your lab 3. Like your lab 3, they don't actually distinguish between row and column select address, right? But here basically you have that. What you actually do is you place the row address first on the address pin. You have to pull the row, the RAS signal, pull it low, then you know that, okay, the row address is in there. Then you put the column address on the column, the column address on the column, on the address, and then you pull this down. And usually in the microprocessor, the row and column address can be set together, but you need to pull the row address first, then you put the column address, right? Because it has to follow in that sequence. You have to select the row first, then you select the column. Okay, because you have to select the row, because selecting the row is what is going to actually to actually read out the bit onto the bit line. That's selecting the row. So after you select the row, you have all these access, sense, and restore. Then only you can select the column, right? Because you cannot select the column before you select the row and you allow the access, sense, and restore part. Because if you do that, then your output is going to be not really logic, zero logic, or it might be somewhere in between here. It might be a not good logic. So that's why you always have to select the row first, which is selecting which of these bits to update the bit line. Then you give it some time for the access, sense, and restore to happen. Then you go and select which of these bit lines, the column access you want to select. That's why the row and the column access are one after another. And after that, only you have your data that is valid out here. The problem is every single different address you want to read, you have to put in the row and the column address, right? And so if you have 16-bit address, you're actually changing 16 bits in one go. 16-bit for every single address you read. And again, every bit you change, it requires energy. So if you have 16 bits, you have 16 bits of energy changing all the time, and then you have to wait for these long lines to settle, right? Because normally the SDRAM is actually, the DRAM is actually a chip, so your signal will come from another chip, so you're actually going onto the board and all that kind of thing, so the wires are actually really long compared to the wires on the chip, so it's going to be really slow. And what's going to make it even slower is because you've got 16 wires in parallel going one go, so those wires will have inductive coupling, capacitive coupling, so you cannot run them too fast. So this is what makes this kind of asynchronous DRAM really slow. And what people have done, okay, what the industry has done is they got this brilliant idea. They said, well, if I'm going to actually choose the column address, and you notice something here, you notice something that when I choose the word line, all the bits in that row are being fed into all the sense amplifier, and I'm only going to choose one out of the sense of all the sense amplifiers in that row. I'm only going to choose one to send to the output. So if I actually want to read the bit of the next word line, it's very easy. I only need to change the column address. I don't need to change the row address, and I don't need to change any, I don't need to allow it to do any kind of access, sense, and restore. Why? Because when I do the row access, sense, and restore, it is reading out the entire row. All the bits are going to sense amplifier. So it's already reading out the entire row. Okay, so the way DRAM works is that when I read out, when I send the row signal, I'm reading out the entire row, and then I'm only choosing one bit out of the entire row out. So if I want to read fast, I can actually read the entire row much quicker than if I were to read a bit from consecutive or different rows. Do you understand this? This is a very, very crucial point.
Can you repeat it again, sir?
Okay. The point here is I have already described to you that we access one bit by choosing the row, and then it does the access, sense, and restore, and then every bit in the row is going to put at the output already, but it's not all going to the output. I need to choose one bit out of this. Okay, so if I want to pick this bit, right, the way it works is I have to choose the entire row. That means this entire row is all gone into the sense amplifier. There are 8 bits in the sense amplifier. Then once the 8 bits are access, sense, access, and then restored, okay, I'm only going to choose one of the 8 bits to send as a one bit, which is this one. But then I've already read the other bits. Okay, so if I want to read this bit, 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 if I want to read this memory in this sequence, it's actually really fast because I only need to choose the row access once. All the bits are going to be read out simultaneously into the sense amplifier, and then output of my pin, I'm going to choose using my column address, the first bit, the second bit, the third bit, the fourth bit, the fifth bit, the sixth bit, the seventh bit, the 8th bit. I don't have to go through the row access for each bit. Because of the nature of the DRAM, it always reads out the whole word line into the sense amplifier, and then it chooses one bit there. So if it's already there, I can actually just be faster and actually read out consecutive bits. Do you understand that part?
Yes, sir. Yes, sir.
Okay, if you understand that part, then this comes to the interesting point. If you want to save some time and you don't want to keep changing this, why not just get a burst of data from the DRAM. Don't have to read one address, because if you read one address, you have to do the row select, then the column select, then the row select and column select. So if you happen to be reading the entire row like that, you're doing row address and column address, then row address select and column select, then row select and column select. But you don't need to, right? Because when you did the row select for the first bit, you have already read out all 8 bits in the sense amplifier. So there's some scope for us to actually speed this up, and that is recognizing that it's quite useful. Actually, we can actually just read up a burst of values, bits in sequence like this. And if you remember from computer architecture, you remember your temporal and spatial locality, right? This is spatial locality, right? So spatial locality is quite important in memory accesses. So you also want to read out in a contiguous fashion anyway, right? So this is what we're recognizing. So now we're saying that to make things faster, we introduce the concept of synchronized DRAM or synchronous DRAM called SDRAM. Earlier, I was just talking to you about DRAM, dynamic RAM. It all comes out from the fact that you have this one capacitor and one transistor. Now I'm saying that to speed things up, what we do, we have synchronous DRAM. What is synchronous DRAM? We add in a clock. Data is read out every clock. So you only need to read the row address once, and then the column address, and after that, there will be a burst of data coming out, a burst of bits coming out. Why? Where does this burst of bit comes out? It comes from the bits that are sharing the same word line, the bits that are sharing the same word line. That is, all these bits are going to be read out in sequence. And what is the synchronization? In what sequence is going to be controlled by the positive edge of the clock. Okay, so you put in the row address, the column address, then the clock, at every clock edge after that, you come up the first bit, the second bit, the third bit, the fourth bit within that row. You got this? This is the innovation of synchronized DRAM. And they don't require you to update the column address or the row address, because internally they will store the column address. And then when you're reading this out, there's an internal counter that will increment the column address and choose it. That's why we have these extra funny circuits here. We don't just have the decoder to choose the row and the multiplexer to choose the which bit. We also have a row address buffer, clock generator, and a counter here, so that it can actually count which column to go, right? So that you can have actually this burst of data out. Okay, so modern SDRAM device you don't just put one address, you get one value out. You have this kind of modes where you can read 4 continuous bits, 8 continuous locations, 16 continuous locations. This is called the burst length. So you can actually configure the burst length so that you can read a sequence of locations or boxes from the DRAM in one go. Is this clear or not?
Yeah, understand.
Okay, understand, huh? Okay, good. Now, how is SDRAM different from DDR RAM? DDR stands for double data rate RAM. Double data rate dynamic RAM. Okay. Nowadays, your memory from your computer is all DDR. The only difference is instead of reading the data at the post edge clock, DDR, the data of the burst data is actually set up at every clock edge, on the positive edge and the negative edge. That's the key difference. Okay, so DDR RAM is quite similar to synchronized DRAM. It's using the same concepts, except that the data is being set out at both clock edge. So you get the first bit on the positive edge, and the second bit on the negative edge, the third bit on the positive edge, the fourth bit on the negative edge. So it's faster. Okay. That's the main one. And I want you to recognize that this data output pin is called the DQ pin. Okay, just recognize that. Okay, so we have come to the reason why you're now looking at this is what we call a SDRAM device. Like this is called a page mode device, but we're not looking at page mode. We're looking at more like this, a SDRAM device. So I put this out from Micron. It's a 64 megabit DRAM. And you can see that this is the DRAM array, the sense amplifier. Then of course this one is the multiplexer, and then the column decoder. See the address is actually split into a row decoder and a column decoder, right? 12-bit, 10-bit. So this one actually has to the power of 12 rows, and this one has to the power of 10 columns. So you can actually draw the organization of this, okay? And there's some additional logic and the counter here. The counter allows us to actually count to go to different rows, and we're also able to do a burst from the column decoder here. And this is just a multiplexer to go either you're sending data out or writing the data in here. But there is a state machine, a controller here that will receive commands and then decide what is the operation. And we're going to go through this in some detail. And your role is actually, this is the chip given to you. This is the chip on the FPGA. But unfortunately, I can't access the system, so I can't get the actual data chip, data sheet. So that's why I ask you to help me get so that I can share it and we can discuss with the actual chip. But for now, I just let you know this is an equivalent, but you expect something like this, but you still have to go and fetch the data sheet of the one in the FPGA. So what you need to do is actually you need to design some circuit outside of here to control all these pins so that you can give it the commands to control the address and then to control the data so that either you can read or you can write into this SDRAM device. Okay, that's what you need to do. Okay, now we're going to go to the second portion of the lecture. We covered the first portion of the lecture, which is you now understand the basics of DRAM and what is synchronous DRAM, SDRAM, and why a little bit more or less why it's so it's a bit complicated to read it. It all comes back to the point that it's just one capacitor kind of bits, right? That is a key point. Why is it so challenging and all that? And it's because of the way it's organized. You have the row and the column select, and you're trying to get a very fast device. You have to do all these fancy things. Now we talk about how this SDRAM is actually organized to give you your 64 gigabytes or 32 gigabytes of memory in a CPU. Okay, and why am I talking about CPU in the digital design? Because most high-end design today is actually some form of CPU or another. It's more or less similar. You have a controller, you have a bus, you have commands, and then some things that pipeline and all that kind of stuff. You can't run away from it. Okay, people don't really design 7-segment decoders and all this. It's like all very easy stuff. They don't even design adders anymore. Those things are really all well optimized to death already. What they're designing is interface circuits, how to connect known logic blocks. They call it IP sometimes, intellectual property. How to connect all these IP together, put it together so that you get a functional chip. That's why we're focusing on interface, and SDRAM interface is one example of a pretty complicated interface. The other types of interface would be your PCI Express and all that. Okay, so now I'm going to talk a little bit more about DRAM organization. How are we organizing these chips in a system so that you can actually see the full breadth of the complexity, why we need to do all this, why we need to figure out all this, because it's not, the storage doesn't just end there. It gets more complicated because within the DRAM chip, you have something called banks, and you also have something called ranks. Banks and ranks. This is just how DRAM is organized, because you will never find a 64 gigabyte DRAM chip. You will never even find a 1 gigabyte DRAM chip. I guarantee you that. Okay, if you do, technology has moved a step up. Okay, the reason why is because there is a fixed size at which they can build the DRAM array. Bigger than that, the bit line and the word line capacitance becomes too large, and then it will slow down the chip. Okay, let me repeat that. They are not, people are not going to build a DRAM array about 32 gigabits or 64 gigabits. Why? Because there is a sweet spot, maximum size of your DRAM array. Above that size, the bit lines and the word line, the capacitance of the bit line and word line becomes too big, because again, the bit line has to go through all the bits in this column, and the word line has to go through all the bits in this word. And as you saw in this Micron data sheet, there are 2 to the power of 10. That means there are 1024 columns. To the power of 12, there are 4096 rows. That means the bit line actually has to pass through, has actually 4096 transistors and capacitors attached to it. and the word line has 1024 transistors attached to it. Okay, that's how many it is, and it's very long and it's got a lot of capacitance on it. So beyond that size, you're not going to find a very large block. So what people usually do, there's a sweet spot. Normally it's about 256 or 64 to 256 megabits, some around there. And then they keep it there already. And then what they do is they start assembling a bunch of these chips together to make up your 64, 32 gigabytes or gigabits. And now we're going to understand how they do it. So for example, what you're used to is in a computer, if you open it, you're used to this. It's called a DIMM, or it used to be a SIM, but now it's called a DIMM, DIMM, dual inline memory module. Each of these black things is an SDRAM chip. So there's 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 SDRAM chips here. On the other side, there is another 8 SDRAM chips. So there's 16 SDRAM chips here. So for example, if this DIMM, okay, this is a bit of old technology, like if it's 128 megabyte capacity, if I've 8 of these, then I've 8 times 128 lah. So that's roughly about 8 times, it's about almost about 1,000 lah. It's about 1 gigabyte lah. So on both sides, if each of these chips is 128 megabyte SDRAM, and I've got 8 on this side, 8 on the other side, 16, this is a 2 gigabyte SDRAM. Okay, and each of these chips, actually the device density is 64 megabits. There could be there's a certain number of rows, certain number of columns, number of banks, and device width, device per rank, and number of ranks. Let's talk about that. Okay. Okay, just to show you, let's say for a 256 megabit SDRAM, that means this SDRAM has 256 million bits. That means there are 256 million boxes. Each box can store 1 bit. I have few configuration. I can have 64 million boxes. Each box stores 4 bits. Okay, which actually means I've got 64 million boxes, 1 bit each, and then I got 4 of them, and then they are read out simultaneously to give 4 bits. Or I can actually have an arrangement where I've got 32 million boxes and there are 8 of them, so they're read out in 8 bits, or I've got 16 million boxes read out 16 million bits. Okay, so I've got different versions of that. And if I'm actually using 64 million, I could have 8,192 rows. Okay, but within the rows, the word line itself, if I got 64 mega boxes, then it's 2048 lah. If I got 32, it's 1024. If I got 16, it's 512. Because again, I got a fixed number of bits. It's just how I want to arrange them, and how whether the data bus is going to be 4-bit out, 8-bit out, 16-bit out. So I just want to alert you that different SDRAM chip, okay, for the same capacity, can have different arrangement in terms of different number of rows and columns for the same number of bits. Okay, so just aware of that. So a single DRAM array, which we talk about, 1 bit per box lah. So there's a row and a column organization. Okay, and this array, this is called a DRAM array. I parallelize it to get the bit width. So if you see from the data sheet X4, X8, it means that chip actually has a 4-bit output or 8-bit output, because the array is actually parallelized. And the rows are actually the word line. So this is 1 row, 1 word line, and the columns are actually the bit line. 1 column is 1 bit line. Okay. Again, this is the data sheet. This data sheet, again, that's 64 megabits array. I can actually have a times 4, that means a 4-bit out, times 8, an 8-bit out version, or times 16, a 16-bit out version. So I've got several different organizations as possible. So this example of a times 4, 4-bit out, I have 16 mega bits per array lah, and then times 4 of that. Okay. Okay. Now, this is going to get a bit tricky. This is one DRAM chip I'm showing you here. Okay. What do you mean one DRAM chip? One black thing here. So there are 16 of these, 8 on one side, 8 on the other side. Inside one of these, you have this. Okay. I already told you that you can actually have different type of data width times 4. That means 4-bit out, times 8, 8-bit out, times 16, 16-bit out. Is times 4 means there are 4 of these arrays and they are actually having the same row and column. So if I'm looking at times 4 and there are 4 of these, the 4 of these grouped together is one bank. I can have multiple banks within an IC. Bear in mind, I can have multiple banks within the IC, but one bank is a set of parallel DRAM arrays, right? So the DRAM array, if it's 4-bit width, that means there are 4 DRAM arrays. They all share the same row and column decoder. I have 4 banks within the chip. Each of these banks will have a different row and column decoder. I repeat that. I have 4 banks in a DRAM chip, SDRAM chip. Each of these banks will have a different row and column decoder, which means that I can access the data in each of these banks simultaneously. Which means that this is actually a way of pipelining memory accesses. Just as you can pipeline instructions to a processor, I can now pipeline read or write instructions, right? Because each read or each write is an instruction. Okay, I can pipeline the read and write instructions to different banks within the same DRAM chip. What do I mean by pipeline? It means, you remember there's a row access, then I have to wait for, I have to do a pre-charge, then I do the row access, then I wait for the access, the sense, and then the restore, and then the column, and then the output data register, right? So it's a long process. So in order to cut short the time, I can actually pipeline it, meaning that maybe the first bank, I can do the row access. After the row access is done, I'm actually doing the pre-charge is done. I actually want to do the access, sense, and store. So while I'm doing the access, sense, and restore of the first bank, I can start the pre-charge of the second bank, which is using a different address. Okay, so having multiple banks in an SDRAM allows me to pipeline different memory accesses so I can speed up and increase the throughput of my SDRAM. You got me? Is this clear?
A bit hard.
A bit hard. Okay, let me try again. Okay. This one, you understand why we need multiple SDRAM chips in a module. Do you understand that? It's because we don't really want to build too large SDRAM chips. Is that clear?
Yes.
Okay. Is it clear? I tell you that this is a 1-bit DRAM array. If I want to get a times 4-bit width, I just have 4 of them in parallel. Or I want to get times 8-bit width, means I have 8 of them in parallel. Means the output is 4 bits or 8 bits. Is that clear?
Okay.
Yes.
Can. And is it clear that I tell you that, let's say I give you one chip, right? One chip. If that chip has 64 megabits, right? That means that chip has 64 million bits it can store. There are different ways I can organize it, different number of rows, different number of columns. And one of the ways is by specifying whether the output is 4 bits or 8 bits or 16 bits. You can get that?
Okay.
Can, right? Because not too difficult, right? Because it's the same number of bits, just whether I choose to have them to be 4 bits in the output, 8 bits in the output, 16 bits in the output, and then I just reduce the number of columns. That part is clear, right?
Okay.
Can, Okay, great. So you haven't lost too much actually. You just got lost at the bank part. Okay. Now, let's be clear lah. If I have a times 4, that means I have 4 of these DRAM arrays in parallel. That is one bank. Just get that terminology right. That's one bank. Can you understand that?
Okay.
So when I want to access one bank, it means I'm reading 4 bits at one time. Storage of 4 bits, not storage of 1 bit. Correct? Okay.
Okay.
So if it's times 4 means I'm reading a 4-bit bank. If times 8, I'm reading a times 8 bank. Okay. But actually what happened is I'm actually reading 4 DRAM arrays at the same time. So the row address and the column address is going to exactly the same location. I mean, but in a different array. Correct? You agree with me?
Yes.
Okay. Which means I have to read. If it's a 4 array, that means one bank, I have to read all the 4 arrays at the same time, at the same location, everything. Okay, right? Because the data is grouped together, right? It's a 4-bit bus, right? I need to group these 4 arrays in order to get 4 bits, right? Or I need to group these 8 arrays to get the 8 bits, right? But I'm accessing the same box within all 8 arrays. That part is clear, right?
Okay.
Okay, now I'm a very impatient person. I cannot wait for pre-charge to happen, access to happen, sense to happen, restore to happen, right? I was so impatient that I couldn't even wait. I was so impatient that I couldn't even wait to actually put row and column address, such that I needed to do this, right? So I'm very impatient, right? Very impatient. I don't want to wait for all these, what I'm doing like that. So what I'm saying is that, again, is this idea of pipelining. The idea of pipelining is that you actually have an operation that is taking a long time and is using different parts of the circuit. So I can actually do in parallel, but not exactly at the same time. I just start one task first. Then as that task go on to part B, I can start the second task, part A. As task 1 goes to part C, task 2 can go to part B, can start task 3 in part A, right? So it's something like saying that, like what we're doing, right? Like I'm assuming that you are using different parts of your brain to learn Dr. Pangizu part and my part, right? So he hasn't finished yet, but you're moving to his task C, lab 4. So you are starting my task A, because we are assuming you're using a different part of your brain, okay? That's pipelining. So we're not actually increasing the speed. You're still learning. It takes you up to the end of semester to learn, right? It doesn't take you 1 month to learn. You're still learning it up to the end of semester, but we're increasing the throughput. The content you learn at the end of semester is more. Do you understand that? That's pipelining. Do you understand that?
Yes.
Okay. So I want to pipeline this, and I'm telling you that the read process, the pre-charge, the sense, the amplify, and the restore, the access amplify is a very long process, right? So the way I do that is I said, instead of one bank, I'm going to have 4 of them. Okay, so one bank can output 8 bits, for example. So I'm accessing one bank, right? And when I access that, I need to do the pre-charge first, then I need to do the row access, then I need to wait for it to access, to sense, to restore, then it reads out to the sense amplifier array, then the sense amplifier, I'm going to use the output to the column decoder, and then putting into the data out, right? So what I'm saying is that if this thing is being sent at the output to the column decoder, if I'm actually tuning the column decoder, I can actually start the pre-charge process or the row access process, the sense, amplify, and restore in bank 2, right? I don't have to wait until everything is out before I start the work in bank 2, correct?
Yes.
Okay, so you can think about it as a bank is like an independent DRAM lah. You can think about it as that I put it in the one chip lah. Okay, right? So earlier on we said that one bank is basically a bunch of arrays. Okay, each array is 1 bit, but I have to group them in order to get 4 bits or 8-bit data lah. So all of these I call one bank. So a bank is like an independent set of kotak that I can store. Okay, but in this set of kotak, I can only pull out one data at one time out of all the kotak. Okay, right? Because I only can handle one address, and it takes me some time It's like I'm going to look. So it's like saying that, if you can imagine this I have one post office. Inside the post office got many kotak, right? And then I only got one person who is fetching the mail from each kotak, right? So if I want to fetch my mail, someone has to go and ask that person. That person fetch from one kotak, then come back, right? So there are so many kotak in that post office, but because there's only one person serving, you can only check, that person is only going to check one kotak at one time, even though there's so many kotak, right? So that's one bank. One post office is one bank. Now, if I actually want to speed things up, I will actually build 4 post offices. Each post office will have its own person. Okay, so if I'm looking up maybe one box in post office 1, I can also look up a second box in post office 2, can? It's possible, right? Because each post office got its own person. Do you understand me? That's okay, the analogy? Okay, so let's say, for example, that I have only one mailman. that means it's going to the post office. I have someone to collect, right? That one person is going to collect from all 4 post office. Okay, post office 1, post office. This is your data out bus for read operation. Okay, so I have one person that can go to the post office and tell which surat or which address I want, and one person that can collect from the post office. But I got 4 post office, 4 banks lah. Okay. So the first person can go to post office 1 and say, okay, give me the content from box number 5. Okay. So the fella in post office 1 will just go and catch box number 5 lah. Does my person have to wait for him to finish? No, right? Can actually go to post office 2 and ask, right? Because he's already looking for it. He doesn't need you already. So that's why we have 4 banks lah, because you can actually send the command for the next address to a different bank. But I cannot send it to the first post office lah, because the first post office haven't finished. If I ask him for another one, it's going to get confused, right? So the way to parallelize it is, I have my runner pergi to post office 1, say get me from box number 5. Then okay, the fella goes to the back, banyak peti there, 6 million peti, right? To check one by one. I will go and find. I have to go to which row, which column. It takes me a while to walk there because very, very large. Then while he's doing that, he's doing his row access and pulling it out. My runner go to post office 2 lah and say, now I want from box 16, post office 2, right? So the post office 2 punya runner, postal worker will start to go into their big post office vault. Wow, that's 6 million again. I go to row and all that. But while he's looking, post office 1 already fetched already, and then can give it to the first runner to the runner to actually deliver, right? Because there's only one delivery person. So that's the output bus. So can put it out of the bus. So by the time that fellow deliver, post office 2 already finished, ready to give to the runner. So you see, the runner is just what the runner is saying is like, oh, I just, as soon as I get from post office 1, then suddenly post office 2 is ready. So it's like very fast. But if the runner were to wait for post office 1 all to finish deliver, then only the runner will go to post office 2 and request, and lama kan? Okay. Do you see how this is used?
Yes.
Okay, so we have banks in order to parallelize the accesses, and this is where the command comes in lah. You can start overlaying. Just because your first read or write command not yet finished yet, you can already send the next one, and that's why you have some kind of decode logic to be able to receive that. Do you understand that? That's all. That's why we need the banks to be independently addressed. That's why the banks will have a row address latch, because it needs to remember, right? If the first bank is bank 0 is already fetching something, then you had a new address come in. You know, it shouldn't corrupt bank 0 lah. You should remember the previous address and you should only send it to bank 1 and things like that lah. Okay, right? So this is the bank architecture. Now it's going to get more complicated. Within one chip, there are multiple banks. Okay. But as I told you, within one bank, there's like times 4, times 8, times 16. That's only 16 bits, ma. Nobody builds a 32-bit bank. So in order to get 32-bit banks, you need to group 2 16-bit banks or 4 8-bit banks together. You got it?
Can you repeat, sir?
Can. This is very confusing. But you have this recorded video, and if you can get it, it'll be good lah. Just now we talked about banks. Banks is allowing you to access different addresses during a pipeline. So you can access it in parallel, simultaneously, different addresses. Not in the same array, but different address. And we talked about one bank could have 4-bit output or 8-bit output. Okay, but 4-bit, 8-bit, 16-bit, if you look at the data sheet, the maximum you see is about 16-bit. Very few and almost very hard to find 32-bit or 64-bit banks. Okay, but then your computers are all 32-bit and 64-bit. So how do you achieve that? You take 2 16-bit banks, chips, and you use them together. One is addressing the lower 16-bit, one is addressing the higher 16-bit. You got it?
Okay.
Okay, so it's the same thing like array. I group them together to make one bank, except now I am grouping chips to make them one rank. So I all the chips in the rank will form the full data word. Within each chip, there are banks, okay, which means that this chip can actually have 4 words being fetched simultaneously. And again, because all the chips in the same rank, each of the banks work together, like the bank 0 from here, from here, from here, from here, from here, all have to work together because they are from the same rank. Okay, so rank is a way to supplement the data, the DRAM array, to get to very large word width lah. So this is about 32-bit, 64-bit, 128-bit. Okay, and why don't you have 32-bit width? Why? Because I think 32-bit width, too many DRAM arrays in parallel. So when that happens, again, capacitance slows things down and all that. So there's a kind of like a sweet spot. Up to about 16 bits, 16 bits with 16 bits is enough already, right? It all goes back to speed. Okay, so now I'd like you to know we are assembling multiple DRAM chips, SDRAM chips into one rank. This one takes maybe the first 8 bits of the 32-bit word, the second 8 bit of the 32-bit word, the third 8 bit. And within each chip, there are multiple banks, which they can be done in parallel, and so on and so forth. So rank, because they are all part of the same data word, all the chips in the same rank must have using the same address lah. But those address can be pipeline lah. If you're going to bank 1, bank 2, bank 3, bank 4, they can be pipeline, but they have to be the same address. Okay, right. I'm not going to belabor this point because it's just the organization. Okay, so the way it works is in one DIMM. Okay, in one DIMM, most likely this is one rank. Okay, 1, 2, 3, 4, 5, 6, 7, 8. If it's a 64-bit, most likely this is a times 8 output lah. So there are 8 chips. This forms one rank. Usually one rank can be one channel lah, right? So you will have channel, ranks, and banks in SDRAM organization. Okay, so what happens is it used to be there's a memory controller like this, and then you have the first DIMM, the second DIMM, the third DIMM. And then the graphics card, you have a memory controller directly on the graphics card. So what they actually do is, nowadays, within your DIMM, there's a memory controller already that will take into account and connect up all the individual SDRAM chips so that they function as one. You will be designing not the memory controller, something else out here to talk to the master memory controller to read out from this. But I'm not making you read out from multiple DIMMs lah. I'm just making you read out from one chip lah. Okay. All right, now we come to the configurability of the interface. So you, just like your microprocessor, microcontroller, you have to set up your registers and all that, right? You have to set up the configuration bit. So you also have configuration bit for SDRAM. You can actually change the burst length. Okay, what do I mean by burst length? Burst length means, are you reading 1 bit in a row, 2 bit in sequence, 4 bit in sequence, 8 bit in sequence, 16 bit in sequence, or the whole word length? Okay, so the whole word length is called page. Then you got 1, 2, 4, 8. You can set this by just setting a register within the SDRAM. The cache latency, the column select, that goes to mean that how far apart is the latency between the update of the data. Is it 1 clock cycle, 2 clock cycle, 3 clock, 4 clock cycle, 8 clock cycle? Right, so that's what cache latency means. Is it 2, 3 clock cycles, 4 clock cycles in between? Okay, and the burst type, whether it's sequential or interleave. Sequential, you know, the first bit, second bit, third bit, fourth bit, fifth bit. Interleave means it will go maybe the first bit, the third bit, the fourth, the second bit, the fourth bit. You know that there's a certain pattern, and the way you can do interleaving is just because of the memory organization. But just letting you know that different SDRAM chip will have kind of different features on this. Okay, so but you need to be sure you set the registers and you set the proper mode before you start your access. Okay, Ken?
Okay.
Okay. Okay, how are you all doing so far? It's going to get much worse now. All right, so I tell you what, now I'm actually going to go into, gradually going to ease you into the actual what's actually going to happen on the chip, how you're going to actually interact with the chip. Okay, we're going towards that already. And the timing aspect of things, we're going to go to the timing aspect of things. And then we're going to go into the interface. And then we're going to look at actual data sheet ready here. How do you actually do this read, write, and pre-charge operation? Okay. So the goal today is actually to give you this big overview and to get you ready that you say that, okay, after you go through this lesson, you can start your assignment already. You may not know how to program FPGA yet, that will come on Friday, but you will already be able to start designing your state transition, your controller, how to access the SDRAM chip. Okay, that is the goal for today. That is the outcome from today's lecture. But this lecture, I'm guessing you probably still have things that you are not quite sure, you need to listen. And what I would like you to do is I'd like you to get started on the assignment. I'm okay if you all work as one team. Just please know, riders, all of you must understand you can do a different part. Just let me know which part, but work together. I'm fine. I just want you all to have the experience of doing this. And most likely your EA question will be very, very similar to this. So from my part, you don't have to worry. You do the assignment, you should be ready for EA. Okay, that's the deal. Is that okay?
Okay, sir.
Okay, so from my part, from the additional masters component, this assignment for the FPGA, you will be accorded 30% of your coursework marks. And I will also have 1 out of 3 questions in the EA will be from me. But my promise to you is you do a good job on the assignment, you wouldn't need to study at all for your EA. Okay, it's going to be similar. Okay. What I might do is I might just change something here and there, but it's going to be very similar. Okay, right? So you don't have to worry so much about what you need to study and all that. Just do a good job being able to access this. I will have the question to be quite similar. Okay, but simplified that you can actually get it done in a few hours because I know you have 2 hours. You have 2 other questions from Dr. Fauzizu, so my question has to be even shorter Okay, right? But this SDRAM interface design, this is not easy, it's not trivial. Okay, for most of you. I mean, for me, it's okay, it's not that difficult, but for you, it's probably because you're still learning how to do that. Okay, so I'm showing you this because these numbers actually show you sort of the sequence of steps. And here is basically sort of like a timing diagram. Why? Because it's trying to show you, number one, there are timing parameters. There are certain number of microseconds or nanoseconds you have to observe when you're interfacing with the chip, and then this is the numbers, and this is actually showing you here which part of the SDRAM circuit is being utilized. So this part here you actually can see is, you can think about it as the pipeline. This is like a 4-stage pipeline. You have the first stage, second stage, third stage, fourth stage. Okay, and this is in time. So in the first stage, you have a certain amount of time that you're allocating to give the command. You're giving the command to here, and the way you give the command, we'll go through this, is you set a bunch of input and output pins. Usually is the RAS, CAS, write enable, chip select, and CKE. You set them to a particular format for a certain period of time. Then that means that the chip has received that command. So this pattern here represents a command, and there are certain commands you cover. There's a row access, a column access, a pre-charge command, and then you will need to combine all these commands together to get a read cycle or a write cycle or a pre-charge cycle. Okay, so this is example of a read cycle. So first you do this command. After you put the command, you have to wait a certain amount of time. There's a certain amount of time after the command decode is done over this time. It will go to phase 2 where it's actually accessing the DRAM arrays. It's going to do the pre-charge. Then the pre-charge is already done already. You always do the pre-charge before at the end of any command, right? That's what you always do. So you will do the access, the sense, and the restore. That's number 2. It takes this amount of time. So after the restore, when the restore is being done, the column access will start activating the multiplexers. This is called device utilization at the level of the individual chip. And then at phase 4, this is the bus, how it's actually being transmitted on the serialized data bus. So this is the 4 phases of the pipeline. general how these commands are actually propagated lah. Okay, so the SDRAM chip, there are just a few basic commands, and I just want to focus your attention lah. There are actually 3 basic commands only: row access stroke, pre-charge, column access stroke. They're just 3 basic commands, but you string together the sequence of commands in order to make a read cycle. And you string together the same sequence of commands in order to make a write cycle. And you string together a sequence of command to make a refresh cycle. So on the low level, there is commands. You issue commands by putting a certain pattern of bits onto a set of data lines. And then you put together a sequence of commands in order to generate a read cycle. Okay, you got it? So I'm just going to only focus on 3 commands. That some SDRAM devices would have more fancy commands and all that, but these 3 are the basic. The row access command is basically you put the row access command, there's a data sense, and then there's a certain amount of time when the data comes out. The data is restored. Okay, because it's row access, it's not actually reading anything, it's just doing the data sense and the restore lah. Okay, so here you just looking at here because I want to show you the time lah. There's a data sheet is full of all these kind of abbreviations on timing. You have to respect this lah. So if you know that T row access time, access stroke is this time here, the total amount of time for it to sense and to restore to the DRAM cell. A pre-charge command, the pre-charge, remember the pre-charge step. Okay, let me go back here. Row access stroke is these 3 steps, 1, 2, 3. Pre-charge is this step, that is you just setting the 2 bit lines to be the same VREF lah, at BDD over 2. Okay, so the pre-charge command is basically you have to put some kind of pre-charge command here, but is usually about the same time as the row access stroke lah. And then there's a certain amount of time for the pre-charge to happen. And this is the total amount of time TRC lah. Okay. And the column access stroke, there are 2 versions of it lah. One is for reading and one is for writing. Okay. So the reading one is you have a column read command. Okay. Then the data is being read, the first one, then the second one. So depending on the first, whether how many of this depends on the burst. How many are you doing? A burst of 1, a burst of 2, a burst of 4, so on. Okay. And the write is also similar. You have the column write command. Then the data bus, because here you are actually reading from the array. So you have to fetch from the array, go through the sense amplifier, go through the decoder, the IO, then go to the data bus. Here you're actually receiving the data from the bus and putting it in the array. So you actually utilize the data, the burst on the bus first. You go through the multiplexers and decoders, then you go through the banks, the bank access. Okay, this is just giving you the timing. Okay, so now how do I perform a read? I have to tell you all that because now I'm finally getting to how you perform the read. A read is actually you put the row access command, you let it finish RCD, okay, and then you can start the column access command in such a way that the column read must finish just about TRCD lah. Of course, can you have column read happen a bit later? You can, but this is the fastest you can go. So you have to give a row access command, a column read command, followed by a pre-charge command. These 3 commands respecting this timing is called a read cycle. This is what I mean by implement a read. This is the amount, the type of instructions, commands, and the timing you have to respect to fetch one data or maybe a burst of data from the SDRAM to whatever your application. This is first part of your application, your assignment. Okay, you have to implement a circuit that can talk to the SDRAM chip, which literally means you issue a row access command, a column read command, and a pre-charge command respecting all this timing. You also need to do a write cycle, which is basically nothing else but a row access command, a column write command, and a pre-charge command. So you notice the pre-charge command always comes after the write cycle, right? Because you never know, right? As you see, when you write, you actually don't need to pre-charge, right? Because as we went back here, we were talking about this operation. When you write, you don't need to pre-charge, but the reason you always pre-charge is because you want to keep the SDRAM in readiness for read. So you always, after every either your read cycle, write cycle, you always pre-charge because you want to keep the bit line ready for a read operation so that you can straight away start with this part here, the row access stroke RAS. Why you always end with the pre-charge. So you have to implement a read cycle, you have to implement a write cycle, which is nothing else but row access command, a column write command, and a pre-charge command obeying this timing. And you have to implement a refresh cycle. A refresh cycle is, let's say there's no read and write. The bits in your SDRAM must be refreshed so that they don't leak and lose their value over time. So literally, you have to go in after a certain regular interval to refresh every single bit in your SDRAM. You have to do that. Okay, and it's nothing else but a row access command, right? A row access command to all banks. Okay, but there's some special instructions and all that. But I would like you to focus on the read and write cycle first. Okay, if you don't get the refresh, we can talk about it. Maybe if you already don't have time, I can throw it out the assignment. I don't grade you on that, no penalty. But I want you to at least achieve being able to program and design and program a circuit and demonstrate it. You can read a data word from the SDRAM, and you can write a data word to the SDRAM. Real chip on an FPGA, and you are designing the FPGA part to talk to the SDRAM given its concepts. You are not implementing all of this. This is already in the SDRAM. You're not implementing all of this. This is already the SDRAM. You're not implementing any of this. All that we talked about, you're not implementing that. But I need to tell you all of that so that you understand why you need to obey all this kind of timing and how the commands you need to send. So I'm telling you all of that earlier so that you can understand why you need to obey this timing and the nature of the sequence of commands. Okay? You got me? Is that okay?
Okay, there.
Okay, yeah? Okay. Great. I'm going to end soon. Not going to keep you too long. I know you're very tired, very long day. All right, so this is the Altera circuit, okay, the FPGA system. I've got it from the data sheet. I've also shared the data sheet on Ulan X, and I really request that one of you, any of you, can go to the system, log it on tomorrow morning or even tonight. We pull out the SDRAM data sheet. It would be great, At least I get a bit relaxed, I know that we can actually talk about the real data sheet, not something I pull up, Okay, so DQ is actually the data line. See, it's a data line. So this is actually, now you understand, it's 32 megabits. All right, it's 32 megabit array, but the data output is a 16-bit. So from this array, you get 16-bit out at 32 megabits. Okay, so the data is 16-bit. Okay, no problem. So there's just one. There's no rank here. It's just one device. But we don't know whether there are banks here or not. We need to look at the data sheet. Okay, and the address is 12-bit. So if you look at the data sheet, you will now know how to split how many addresses. Is it the MSB? Is it the LSB? Is it which is the row and which is the column? You have CKE, QM. This is the upper data and lower data word. QM. This is a mask. This is a special thing. Right? Enable RAS chip select. Pay attention to this because we are going to move on to that. Now, this is what the data sheet say. This is the description of what the pins are. Chip select, clock enable, command inputs, input and output mask. So it's sampled high when you want to access write, and then if you want read. So this one is actually more of like helping you to select high or low whether when you're reading or writing. Okay, and this is the bank address, and this is the address. So bank says which bank you're going to write this, and then this is the address. So there's a bit of complexity here because you get some control over which bank. Okay, now this is how you write a command, right? Writing a command. Remember we said the command, there were three that I actually just highlighted to you. This is basic command, RAS, precharge, cast. And you string together a sequence of command to do a read cycle, a write cycle, and refresh. I'm asking you to implement a read and a write at the very least, and if possible, refresh. So how do you do a write, a cast, a read? Okay, you have a read here lah. Okay, so here actually the command is a bit at the high level. You have read and write. So if in this case, then you just follow this lah. This is actually what you do to do read and write lah. Okay, and this is a truth table. This is if you're in the state lah. So here again, there you see there are more commands. There's a pre-charge command, auto refresh, load mode register, command inhibit, no operation. No operation is the default lah. If nothing is happening, you have to actually keep the chip at no operation, right? Command inhibit is to prevent any kind of command from being sent to this SDRAM lah. Load mode register, this one you probably have to set this as well, because this one you have to set lah, like I mentioned, you have to initialize, config your chip, what's the latency, the burst type, the burst length, and so on. So you probably have to figure out how to do that as well, otherwise it won't work. Okay, so this is a state transition lah, showing that if you are in the read state, if you have this situation, what is option and all that lah. Okay, this is just a truth table, and this again example of the mode register. Just now I showed you this. This one is something you need to set. Okay, this is the mode register. This is an example from a data sheet, but you shouldn't reference this because I say I'm waiting if one of you can help me to get the actual data sheet of the SDRAM on chip. Then we can use that. This one I just pick it up to show you the example lah. You have the cache latency, burst length, and all that lah. Burst type, sequential interleave, and all that lah. Okay, right. This is the timing diagram for read lah. Okay, so the read command is happening on the positive edge of the clock edge. You have to set CKE high, CS low, RAS high, CAS low, write enable high. You make sure you have the column address, you have the A10, and you have the bank address. Okay, so you have to go and figure out how to set this, right? Okay, and then you at the clock edge, at the first clock edge, this is there, right? So this is considered a command, right? So this whole thing is read command. This command read represents this whole thing here. Okay, and then your address is already there lah. Okay, so you have that. Then there is a no op command. You have to put a read command, then no op, then no op, then no op. Then by the third clock cycle, your data starts to come up. All right. But this is this data sheet. You cannot follow this data sheet. You have to follow the actual SDRAM data sheet on the FPGA board on the system club for you cloud. But I'm just showing you this is how to read the data sheet. Yes.
Is it data sheet that I shared in the chat box?
Okay. So you went to fetch for me already. Let me see. Looks like no lah, because this is the FPGA data sheet. No, this is not. This is the FPGA data sheet. I'm looking for the SDRAM data sheet.
SDRAM.
Yeah, so where it's stored, if you go to the system cloud for you, and I'm sorry I can't go because I messed up my system. I'm waiting for Intel to get back to me. I wrote to them on Friday, they haven't responded to me. So when you go in, you actually find that you actually log into a PC, right, a desktop with Windows, right? You have to explore the right directory structure. There's a directory structure for this particular FPGA lah. Actually, it's a Teresic FPGA. It's called the DE1 SoC because this is a very fantastic board. It's got an FPGA coupled with an ARM processor together. Okay, I need you to go and explore a bit. There is a directory called data sheets where they actually will store all the data sheets there of the devices, and one of them is going to be the SDRAM. But you have to actually be a bit careful because there are two SDRAM devices on this board, right? One is a smaller one is the bigger one. The bigger one is linked to the ARM controller. The smaller one is linked to the FPGA. I want you to work with the FPGA one, not the ARM controller, because we are not doing the interfacing with the ARM, but this is a very nice board. You can actually do ARM interfacing with the FPGA. But I'm asking you for the SDRAM, the smaller one. But if you don't know which one, you just give me both. I will be able to tell apart lah and tell you which one to reference. But it's not this one. This one is the one that I put on Ulan X. It's not this one.
Oh, okay.
Okay, but is within that there's one directory called data sheet. Then you will see lah. It's basically it will look something like this. This is an SDRAM chip data sheet. You will see, okay, this is all the part numbers, the different configurations, right? Different configurations. We talked about this, right? And then they also got different speeds, speed grade and all that. So this is what a true SDRAM data sheet looks like. But this is a pretty old one, PC100, PC133, LVTTL. This is at 3.3 volts. And auto refresh, it performs a full refresh every 64 milliseconds. It will refresh 8,192 lines, rows, okay, word lines, okay, and then it can also refresh within 16 milliseconds. This is for automotive application. So 64 milliseconds is standard, JDAC standard. 16 milliseconds is like high performance for automotive, because automotive you have safety issue, you can't afford your bits to be corrupted. Okay, so I took some of these here. I want to show you. So here again, they're showing you like for the 16:6, you have like 4 banks. How does it look? They're just giving you sort of like an example. And then this is the pinout of the chip. Okay, they're showing you a pinout from a BGA package, because they got different packages, right? They can tell you they've got different packages. So you have to familiarize yourself how to read data sheets. Because you're going out to the working world, yeah, you cannot just say, oh, I just can only do whatever I've studied, right? You have the TSOP, FPGA, two different packages lah. So TSOP is probably this one lah, TSOP, 54-pin TSOP. BGA, ball grid array, the pins are actually underneath the chip. Then this one here is the description of that. This one here is the actual physical dimensions of the chip, because there's also normally a mechanical person to lay this out. It's not just like, oh, I just put it anywhere. They draw the PCB, all that. Then again, the range of operating temperatures, all these things. Okay, but the reason I want to show you this is because it's long data sheet, but it's pretty complex. Here I want to show you, this is the command, active command, no op command. So I pulled out the read command was here. Okay, and then the write command is here. I put it out from here. Okay, I put that the pre-charge command is here. Okay, but what I wanted to show you was I actually wanted to show you the timing diagram. That's where you actually have to understand all of these and read this. This is the initialization and the load mode register. So to set this up properly, you need to obey this mode register. To set it up properly, you need to obey those timing. Okay. But this is the part consecutive. So you see there's one set of example for consecutive read bursts, for random read access, for read then write. That means a read command followed by a write command, then a read followed by write command with an extra clock cycle, a read command followed by pre-charge command. I believe you go for the read command followed by pre-charge because that's what I want you all to work on. Okay, you don't have to do all. You just do one, read to pre-charge, write to pre-charge, right? But I just want to let you know that the memory controller will receive all kinds of sequence of commands from the processor. You have a read command followed by write command, read command followed by write command. Because again, this same memory, if you're looking at the 4-core system or 8-core system, like your multi-core system, you can have 4 processors requesting from the same memory. Okay, so that's why you can actually have a read followed by a write immediately. Right, like tak bagi chance one, right? So there are many different sequences. If you're building the actual system, you have to look at that carefully. But for your assignment, please just focus on read to pre-charge not the other else Just focus on read to pre-charge enough, okay? Because that's what we covered, right? Read this one, then covered by pre-charge. Then similarly, the write command. Okay, this alternative bank is if you are doing like super parallelization like pipelining, you want to read words from different banks. This is for high performance, and then this is for reading continuous page bursts. That means you are like practically reading the whole memory, but it's how to read this fast. Okay, so there are different variations of these read sequences. But I want you to focus only on one to implement read to pre-charge and write to pre-charge. These two are the main ones. All 4 of you work together, one solution, test it out on the FPGA, show me it works, show me simulation. Okay, so the focus basically, you have to understand what we covered today. You have to study the data sheet of the SDRAM on the FPGA, and you start your design already. Any questions, you ask me. And then hopefully by later this Friday, I will cover on FPGA. But I'm a bit handicapped. I'm not able to show you the UCF and all that but actually it's quite straightforward. As long as you can simulate your design, you can synthesize it, it's already okay. The only extra thing you need to do is you need to specify which input pin go to which output pin of the FPGA. That's all you need to specify. The additional, the rest all, if your design is not too complicated, it will fit into the FPGA. If it's too complicated, then you have problem lah. So again, this is with the pre-charge, single read, single write. So up to you lah if you find that you want to do a single read, but I recommend just do the burst lah. If you read a group of 4 is enough or something like that lah. So you need to capture all of that and display that in your FPGA lah. So you just design a circuit around that. And it's very interesting because when you're able to at least do a read and write, you go for interview with Intel and all that, you can tell them I've done this project, this is how I've done it and all that. I think you have a lot to say, a lot to share. Not maybe the full thing, but you're already along the path that you can actually handle the memory interface, which is what we call the front side bus in a CPU lah. You're already along that path already. Okay, this is the reason for this project. And the reason is also because nowadays, as I tell you, adders, all these computational circuits is no longer the trend to design them because they are very well designed. Now it's more of, we talk about interfaces lah. The high end, you have the router and the switch and the packet networks. At the lower end, you have the buses, and of course, like memory is a very special class of that lah. So this is just showing you again, just reminding you the pre-charge command. I think it's this one. I'm not exactly sure. You have to check lah. It's this one. Again, this is the command is actually set by a set of patterns on a bunch of lines lah. Okay, so lady and gentlemen, this is actually all I have to share tonight. I was hoping I would have a bit more time to talk about logic design. Maybe I'll do that a little bit more. I'll end with that lah. Okay, how are you all doing your logic design for using Verilog? How do you do K-maps and all that or not? How do you design your logic?
For me, actually, I just refer to the internet and I change here and there a bit. And we didn't really draw the
K-maps.
Yeah.
Very good. You're not supposed to lah. K-maps are useless beyond 6 input pins lah. 6 also very complicated. In fact, most of us will just figure it out lah. Like we just work out the logic. You start from truth table and then you code it up in Verilog. Verilog's supposed to be that. But what I want you to understand is you were taught a very specific way to do state machine. That is, you got previous state and next state, right?
Yeah,
or digital electronics. I want you to break out of that and want you to understand this. These square boxes are flip-flops. Okay, now I've got only 2 flip-flops. And please forget your T flip-flop, your JK flip-flop, or throw all away. In the real world, everybody just uses D flip-flop. And the main reason is because D flip-flop, whatever is at the input is sent at the output. And now you will understand why. A JK flip-flop can be implemented with a D flip-flop with some logic. Okay, your state transition diagram is basically nothing else but saying, I have a bunch of combinational logic. Okay, here's my cloud of logic. I have a bunch of combinational logic, and this combinational logic is driving the input of the flip-flop lah. Okay, and I think you know, right? Every kind of state machine always have this form, right? Combinational logic driving the input of the flip-flop, right? Correct?
Yes.
Right? So you always say that the output of the flip-flop is the state lah, right? And then you have the state assignment problem and all that kind of stuff lah from digital electronics, right? The output of your flip-flop is your state, right? Well, the nice thing is in Verilog and modern IC design, nobody cares about the state assignment because the tools will take care of that. But you need to recognize that all you are doing when you're designing state machine is you're designing the combinational logic. You're not designing any kind of fancy flip-flop. Right? Because basically what you're doing is you're just designing the combinational logic so that it can set what is the next state of the flip-flop that it's supposed to capture. You understand? Do you see that? Your next state logic, you're actually designing combinational logic. That's it, right? Except that your combination logic is taking inputs from the state and taking inputs from something else. Okay, and so this means that your circuit actually, most digital circuits you can represent as something like this. Okay, all right. It's always combination logic followed by flip-flop, followed by combination logic, followed by flip-flop. And then there's if feedback also is combination logic, flip-flop, combination logic, flip-flop, that kind of stuff. And this is kind of nice because if you look at your Verilog block, you have always at pause age clock, right? Then you have begin, then you have end, right? I always like you to separate this out. This is your flip-flop, okay? So you will have a reg A, right? So when you type A equals something, blah, 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 this blah, 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 blah is your combinational logic. Remember that. Then everything becomes easy already. So what you're simply saying is you are saying the combination operator is A plus like C plus D, okay, or you're doing some kind of logic A or B, you know, you can literally just code the combinational logic like this. And if you have a case statement, case A, B, C, then you have one, you have like 3B, so 0, 3B, 1, 1, like that, so on, right? Then you have A, like that, right? This is your inputs. These 3 bits are your inputs here, right? And then this A is just the output here lah, going to this flip-flop, okay? And the nicer way to think about this is, you don't even think about it in terms of logic gates. My favorite is to think about this in terms of multiplexers. Okay, where your combination logic, because you all know, right, combination logic completeness, right, and or not is a complete logic. Multiplexer is also a complete logic. NAND and NOR is a complete logic. You know about that, right?
Yes.
Okay, so this is a multiplexer. Okay, A is whatever C, whatever lah, whatever C, function of C lah here. Okay, function of C is the input of the multiplexer. ABC is the selection term of the multiplexer. If you think about it this way, Verilog becomes very, very, very easy. You are just transcribing this circuit into code. That's all. Okay.
Okay.
All right. Final thing lah. And then if you actually just happen to have like one of those situations where you have something like this and then output like this, then this one you can actually have an assign statement outside here lah. Assign something equals in terms of the flip-flop register value A lah. Sorry, assign F, something like that lah. Okay. That's how I write my Verilog. Okay, you figure out what are your flip-flops. You are just coding the next state. Are you using multiplexers, or can you just directly code the value of the flip-flop like that? That's how you design it. And normally the way I would design it is I would make sure I will code the state and then I'll code the outputs. I will make sure I have two sets lah, to be quite clear. Okay, right, that's how I design it. All right. Okay, so that's all I have to share for tonight. If you have any questions, now is a good time to ask. But if you're really tired, then it's okay. We'll leave it to Friday, or we have one more session maybe next week lah. But I've pretty much covered what I wanted to cover on SDRAM today, and then the remaining is just give you a intro on FPGAs and how to program them. But I'm just more by telling you like what's inside an FPGA lah. It's not that much. Once you understand what's inside, it's basically a lookup table and flip-flops. And once you understand that, you'll know how to program it, right? And why I mentioned that is because what's most important, I said, like, if you can actually simulate your code, you can synthesize your code, the FPGA tool will do everything for you. All you need to know is this pin connect to what pin number on the FPGA. This pin connect to what pin numbers. You just literally have to figure out what are the pin numbers, put it in the pin constraint file, and then you compile this, it should work. If you simulate it correctly, it synthesizes, it should work. Okay, and then just have to watch for timing a little bit only. right? If your circuit is correct lah, if your circuit is wrong, then of course it won't work lah. So that allows you to focus more on this design. Sorry, you're not seeing anything, right?
Yes.
Okay, sorry. What I meant was the important part actually for the FPGA. I'm going to give you the long story lah on Friday, what's the FPGA and all that. But the important part really is you need to know this is your SDRAM chip. It's connected to which pin on the FPGA. This chip, which pin on the FPGA. So you make sure that you have a constraint file that you specify. This pin number needs to go to what signal number, what signal name lah, the DQ, DRAM, DQ signal in the FPGA. Once you set that, that's the most important part. If you set that, usually the FPGA will work lah, provided A, your simulation pass, that means your logic at least makes sense. B, you can synthesize it lah. Synthesize, you don't know anything, you just click on the button, it does everything for you already. Okay, but we're going to talk through the details of what's happening at the back end. You're not going to be doing anything, you're just going to be clicking some buttons. You just need to specify the pins and then it will actually complete. Once you got your Verilog RTL, if it's working, the simulation is working, very high chance you just click synthesis, place and route, it will work. Okay, if you write synthesizable Verilog. Synthesizable Verilog means it's Verilog that can synthesize. If you follow this way of doing things, your Verilog always will synthesize. The problem comes if you try to do funny for loops, if you try to do funny if and else also you have to think about it in terms of multiplexer lah. If condition is true, else condition is false. If you can imagine it in terms of a multiplexer or imagine it in terms of digital logic, it will always synthesize. That is, if you follow this simple recipe, it will always synthesize. Okay, and please don't go and put this kind of delays in your code. This is strictly for simulation. Okay, this kind of delays is not respected by synthesis tool one. It will just use whatever it is and then you have to check the timing and all that. Okay, yeah.
Okay.
All right. Okay, we covered a lot in a short period of time tonight, and I think you're all very tired, but it's quite good that you're able to pay attention. You can access this, you can look this up. I think what I'm looking forward in the next few days, I hope you can review this. I hope you can get started, and I hope you can give me feedback lah. If you find that, okay, you are going to get depressed and like this is just going to kill you and you cannot finish this on time, okay lah, let's talk about it lah. See how to finish this up lah. Simply, but at least you just try, you look at it these few days and you give me that feedback lah. Because you only have up to the end of this month. I know it's pretty short with everything coming together, but you just discuss among yourselves, study it a little bit, let me know. How are you feeling about this? If it's really, really, really bad, you cannot manage it, let's try to see if there are ways to scope it down. But I think I would want to require you to use the FPGA because my argument is this, you already learn how to use Verilog and the simulator from the early part of the SDE. Now you need to have that realism and then this will bring you up to a master's level. Okay. Okay, how are you all feeling?
Quite nervous, sir.
Quite nervous, okay. Yeah. All right, go and take a good rest. Look through it.
But before that, sir,
yeah.
Regarding the SDRAM datasheet, so wait, can I share my screen?
Can? Yes, please.
Okay, so where can I get the?
Okay. Can you log in to the machine?
Okay, wait.
Okay, this is great. Oh, yeah, you guys are so on top of things. So nice lah. I wish more UTP students were like you all.
But actually last week we tried to log into the system, but we stuck at here. It asks for password.
Oh, if you click now, just go ahead. Cannot lah. Okay, scroll down. Click OK. Scroll down. Is there any other choice? Scroll down because this is just a PC. Go down. Other user. Just put guest lah.
Guess.
And click OK. You have to recognize this is just a login screen for a normal PC.
Okay.
It's just a remote. They just use the remote. This one lah. If it works great lah, doesn't work, we have to write Yanming another email because they resetted the system, right? Oh, cannot lah.
Sign in.
Okay, so got problem lah. Okay. Okay, then they have to log in lah. Sign in to another domain. No. Go to other user.
The user.
Then you see sign in to. How do I sign into another domain? Yeah. Okay. If you type that whole thing and look and guess lah. You see the P12 HW44WR.
44W.
ENGPIN.
PIN.
Okay. Backslash. Guess.
Guess.
Try lah. Enter. Try and see. Okay, cannot. Alright, time to write to Yanming. Tak boleh lah. Okay lah. Okay, ladies and gentlemen, like this lah. We try to get this sorted out. Good that you still have your access, but actually we have to let them know that we can't log in lah. In the worst case, if the FPGA is still locked out, then you no need to do FPGA lah, but you still need to design this and simulate it for me lah. Okay?
Okay, sir.
Actually, if we want, we have some FPGAs in UTP. You can use those as well. They also have SDRAM. We have the Terasic boards as well. But I have to look them up lah. Lama tak bertapak UTP, so maybe a bit difficult. But I think at the very least, let me give you some certainty. I would like you to design this circuit and simulate it lah. Any which way lah. Okay? You still can work in group of 4. Okay?
Okay, Doctor.
Okay, thanks, Human. Thanks for at least alerting this. Okay, please don't get nightmares about this. I like you to think about this positively lah. I'm not looking to fail you. I'm not looking to give you a bad grade. I'm not looking at anything. I'm just trying to bring your skill level up to something you can be proud of and that can give you a good launching point in industry. But if really, again, it's good we have started early. It's only the end of the first week. We have another 3 weeks more, thereabouts. And if worst case lah, I probably can consider to accept a bit later. But if you really cannot, but I need you to actually start working on it already. But if you really cannot see a way out, talk to me, and then we see how we can actually simplify this. It will be a bit more difficult to simplify it lah. Maybe we just ask you to do read or something like that. But before we go there, I actually want you to at least revise, understand this material, and try it out lah. Try first lah. Don't say cannot yet. Just try first. Okay. Reasonable, right?
Okay.
Okay, reasonable. I mean, we're working in 4 of you, so have group study. You know, pull out. You can use the data sheet that I have there. You just Google SDRAM, Micron SDRAM lah, and then you just pick the first one lah. It's about the same one lah, more or less. Okay, Micron is one of the largest SDRAM memory manufacturers in the world. All right. Okay. All right. So I said, please don't get nightmares. Please don't feel bad. It's just look at this positively lah. But I know it's a home stretch for you, like very difficult time. It's not ideal lah, but it is what it is lah. Given our structure lah. So you try again. Let me know on Friday. Try to take these 2-3 days. You know, maybe put aside 1 to 2 hours a day. I think it could still be manageable. But I know it's a bit tough. Maybe you can try to meet once on Wednesday or Thursday just to see how your learning is together. You know, just review the video again, read the data sheet, really try to understand. You can browse through the book. Okay, if you understand what I've covered, then maybe you don't have to read the book lah. But if not, just browse through the book, have a bit of discussion, bring your doubts on Friday. And let me know again, and then just try to think a bit, how would you start designing one circuit? How lah? Just try, just sketch something. Don't need to be perfect, and then you just feed back and forth. Your confidence will grow lah as you can tapak on something. Okay.
Okay, Doctor.
All right. Any more questions?
No.
No.
No, Doctor.
Yes.
Okay. Try, like I said, don't stress, don't do anything silly. You know, if you really cannot, come and talk. Come and talk to me. Okay, I'm not out here to fail you. Just want to train you to become a really good engineer lah. That's all. Okay. Right. Okay. Take care, everyone. Then I just wish you good night lah.
Okay, Doctor. Thank you.
Okay. Bye bye.
Okay. Good night, Doctor.
Good night.
Thank you, Doctor.
Okay.
Good
Welcome.
night.